Hello, I welcome you all in this course on power plant engineering. Today we will discuss about the impulse reaction steam turbines. Impulse reaction steam turbines are normally used nowadays, they are normally used many of the steam power plants due to their inherent advantage over the pure impulse turbine. So, today the topics to be covered are the working principle of impulse reaction turbine. We will discuss about again the diagram and the efficiency of impulse reaction turbine and gross stage efficiency of impulse reaction turbine. So, the impulse reaction turbine, as I mentioned earlier also, the pressure drop takes place not only in nozzle but also during the blade passage when the steam is moving in the blade. So, when steam is moving in the blade, blades are airfoil in shape for steam turbines, and the blade cross section does not remain constant. In impulse turbine, blade cross section, not blade cross section, but the space, inter blade space, right? The blade passage, not blade cross section, but the blade passage remains constant, right? Because there is no pressure drop. Because here is a pressure drop, there is a change in the blade passage. Due to this pressure drop, one force is obviously works, there is a will component in the direction of u, that is one force which works due to impulse action. Due to impulse action on the turbine blade, impulse action is same in both the turbines. But here, in addition to the impulse action, there is a reaction also. The force due to reaction, suppose steam is moving over the blades, due to reaction there is a reaction force. There is a will component of the velocity, as you know, which exerts force in direction of u. This is the peripheral velocity direction. Now, if you add these two vectors, then you will get the final force which is working on the blade. The final force which is, so final force is not in the same direction as the will force, right. Now, this force and the force due to change in axial velocity. Suppose in a velocity diagram, there is a change in axial velocity in axial direction. This is V1, this is VR1, and this is a change in the velocity in axial direction. So, Vf1, Vf2, this is xi. So, net force which is working on the disc plus this force will be the gross force which is working on the blade. So, right now we will neglect this. So, net force which is working on the blade is the sum of the impulse force and the reaction force, right. Now, the term comes the degree of reaction into the picture. Next slide will take degree of reaction. Now, what is the degree of reaction? So, first of all, while designing a turbine, we assume or we consider certain enthalpy drop, delta H per unit mass, or m delta H is equal to gross enthalpy change, right. So, this enthalpy change, what part of this enthalpy change is taking place in the nozzle, what part of this enthalpy change is taking place in the passage, that decides the degree of reaction. So, delta H in the blades, delta H total in the stage, or we can say enthalpy change in the blades divided by enthalpy change in the nozzle plus enthalpy change in the blades. This is known as degree of reaction. Degree of reaction is high, it means the enthalpy change in the blades is high. There is a Parsons turbine, in the Parsons turbine degree of reaction is half. So, half of the enthalpy drops in the blades and half of the enthalpy drops in the nozzles. And in regarding nozzles, they are fixed blades which work as a nozzle. So in a Paulsen turbine, there are moving blades which are fixed on the turbine surface, right, and there are fixed blades also. Now these fixed blades are not fixed on the shaft, they are fixed on the housing. So they remain fixed, and this combination of one fixed and one moving blade makes one stage in the turbine. So these plates are fixed and they are extended up to the end of the shaft, where they are very close to the shaft, though leakage also takes place between the space between the shaft and the blade edge. But we try to keep this gap as low as possible. Designer, they try to keep this gap as low as possible. This is the, I'm just explaining the structure of a impulse reaction turbine or Paulsen turbine in particular. So reaction value of R for Paulsen turbine is half. It means when we draw the this velocity diagram for Paulsen turbine, V1, VR1, beta 1, U, VR2, V2, alpha 1 and alpha 2. So when we draw the Paulsen turbine, because degree of reaction is half, then V1 is equal to VR2, VR1 is equal to V2, alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. So these are the salient features of a Paulsen turbine, which is normally used in power plants, and it is a impulse reaction turbine. So efficiency of the fixed blade when they are considered as a nozzle. Efficiency of the fixed blade when they are considered as a nozzle is going to be V1 square minus 5 V2 square divided by 2H in the blade. Phi is carryover coefficient. Phi, suppose, because now what is happening, fixed blade, the steam is coming out with certain kinetic energy, but when it is entering the moving blade, some losses are there. Now in account to those, take into account those losses, the carryover coefficient phi is established, that is equal to V1 square by V2 square. If V1 square means the steam which is entering the stage, V2 square is the steam which is leaving the previous stage, not this one stage. So kinetic energy of that steam which is leaving the previous stage, and kinetic energy of the steam which is entering the subsequent stage, that is known as carryover coefficient, and it is very important phenomena. Very important parameter in designing a impulse reaction turbine. Now we will not go for the derivation because it is a power plant engineering course, so I will not go for the derivation for impulse. I have already done for impulse turbine. For impulse reaction turbine, blade optimum speed is rho is equal to cos alpha 1. If you remember, in the impulse turbine, rho was cos alpha 1 by 2. Now here is the rho is the cos alpha 1, and blade maximum blade efficiency is maximum, that is maximum, is equal to 2 cos square alpha 1 divided by 1 plus cos square alpha 1. That is the value of gross stage, sorry, the blade efficiency. In impulse turbine it was cos square alpha 1, but here it is 2 times cos square alpha 1 and 1 plus cos square alpha 1. So definitely the blade efficiency is more. If alpha 1 is same, the blade efficiency appears to be more in case of impulse reaction turbine. Now if you draw the curve for this, for the sake of comparison between impulse and impulse reaction turbine, if you draw a curve, this is cos square alpha 1 and efficiency, blade efficiency. So, blade efficiency is maximum, this is cos alpha 1 by 2, blade efficiency is maximum. But here the blade efficiency is going to be like this, and it is for the velocity ratio cos alpha 1 only, right. So, we have to maintain the cos alpha 1 as the cos alpha 1. At cos alpha 1, if we take the rho is equal to cos alpha 1, in that case the efficiency of the blade efficiency is maximum, and it is higher than the efficiency of impulse reaction turbine for same value of alpha 1. There are so many other parameters also, I mean, to decide the overall efficiency, but this is one of the major parameter for deciding the blade efficiency. Now, gross stage efficiency. Now, gross stage efficiency, if we rho is equal to cos alpha 1, if we take, then gross stage efficiency of maximum gross stage efficiency of impulse reaction turbine is efficiency of the nozzle cos square alpha 1 divided by 1 minus phi 1 minus cos square alpha 1. Now, phi is the carryover coefficient I explained you earlier, which is not there in impulse turbine, and efficiency of the nozzle, right. Gross stage efficiency of this impulse turbine was simply efficiency of the nozzle multiplied by blade efficiency, right. But here the situation is different, and this is the expression for gross stage efficiency of a impulse reaction turbine. Now, I would like to go for a numerical on impulse turbine, then I will discuss a numerical, because numericals in power plant are not there to just to check your computational skill. The numericals are solved in the power plant just to have physical ideas of the values. For example, the nozzle angle is approximately 15 to 20 degree, you will get certain ideas about the velocities and the angles. So, normally in the power plant we give numericals just to give you the physical idea of the quantities, right. So, you may not later on you may not land up with some absurd value, say diameter of the rotor is 50 meters, rotor diameter cannot be 50 meters, rotor diameter is a maximum is 1 meter, right, or blade height is 3 millimeter, blade height cannot be 3 millimeter, it varies between 30 centimeters, I told you earlier. So, these numericals are given. So, in the back of the mind you retain that these are the values which are close to the actual values, right. So, we will start with this numerical on impulse turbine, that is saturated steam at 1000 kilopascal pressure. So, 1000 kilopascal means 10 bar pressure. Enters a D level steam turbine. D level is this is the level. The level is a impulse turbine, and exhaust at 100 kPa, that is atmospheric pressure. There are 4 nozzles in the turbine, and each one is inclined at 20 degree angle to the plane of the wheel. So, alpha 1 is 20 degree nozzle inlet angle. The average peripheral speed of the blade is 400 meters per second. So, it is already given, u is already given. Obtain the best angle for the blades and the blade efficiency if inlet and outlet angles are same, blade inlet and outlet angle, they are blade inlet and outlet angle. What is the approximate power developed if the area of the throat of each nozzle is 220 mm square. So, there is a problem which has to be solved. It is a problem which is mixture of nozzle and turbines, right. So, first of all we will have to find the velocity at inlet V1, velocity at inlet of the turbine. So, for that we will have to go for nozzle equations. So, nozzle upstream is 10 bar or 1000 kilopascal, downstream is 100 kilopascal, right. So, we will take H1 here and H2 here. So, H1 is saturated steam at saturated steam at 1000, 1000 kilopascal, and that is 277.1, right? And because we do not know the quality at the exit and quality at the throat as well, right? So first of all, we will try to find the quality of the exit. So quality at the exit, if you remember, then we will have to take S1 is equal to S2. Enthalpy at this point, enthalpy at this point, they have to be equal. This is saturated, we can take from the steam table, and this S1 is 6.585. So 6.585 kilojoules per kg Kelvin, right? And S2 is SF plus XSFG. Now S2 we have to take at SF, here SF plus XSFG. That will give you the value of X. So here we are getting the value of X as, I will not do the elaborate calculations, 0.8722. Now with this value of X, we can find the value of H2, right? Now once we have the value of H2 I can write H2 is equal to 417.5 plus 0.8722 multiplied by 2257.4. These properties you can take from here. This is HFG and HF, 100 kilopascal, right? Now once we have the value of H2, H1 is already with us, we can take H1 because it is a saturated steam. So Hg we can take from here, right? And then V1 is equal to under root 2000 H1 minus H2, and that is going to be 391.1 meters per second. Sorry, this is wrong. 884.4 meters per second. So this is the value of V1. Now we have calculated the value of V1. Now we have the U, value of U, value of V1 and alpha. Now we can draw this part of the triangle and geometrically also using the skills of trigonometry, because this is 400, this is 884.4, right? And we can easily find the value of beta 1, because now using the skills of trigonometry we can find, because two arms are known, one angle is known, we can easily draw the triangle. Or using formulas of trigonometry we can find the value of beta 1. Here the beta 1 is 25 degree. Beta 1 is 25 degree. Now after calculating the value beta 1, we will calculate the value of VR1. We can easily find the value of VR1, and the VR1 is 526.6 meters per second. Because once the triangle is drawn, all the parameters we can all easily calculate, right? Now here, because we in the problem it has, if inlet and outlet angles are same, plate inlet and outlet angle are same. In this case, if we take the Vril component of this triangle, Vril component of this triangle is V1 cos alpha 1. If we take V1 cos alpha 1 and multiply it by 2, we will get the Vril component. So Vril component is going to be 862.7 meters per second. Now once we have Vril component with us, now this is about the turbine. Now let us go to the nozzle part. We have to find the throat diameter. We have to find best angle to the blades we have already find, or if the area of throat, power we have to calculate the power. Okay. So, for this we will again go for the analysis of the nozzle. This is 1, 2 and 3. Critical pressure ratio, if you remember, P2 by P3 P1 is equal to 2 by n plus 1, 2 by n plus 1 divided by n over n minus 1, right. And here, from here we can easily get the value of P2 as 577.4 kilopascal. This is the pressure here, right. Now, what we are going to do, from here we will get the enthalpy. Once pressure is known, we will go to this table. For a particular pressure 575, we will take the enthalpy. What is going to be the enthalpy? For enthalpy we need the quality. Say for P2 H2 is equal to HF plus X HFG. We need the quality. We will do the same exercise. Entropy is constant. Entropy is 10 kilopascal is equal to entropy at 577 this 0.4 at this pressure and this pressure. The entropy is same, right. From here there we will get the value of X quality, and using this value of quality, from here we are getting the quality as 0.961. Using this quality we will get the enthalpy at stage 2. When H2 is known, H1 is known, what we are going to do? We are going to get the velocity at stage 2, V2, right. Now, once we have the velocity at stage 2, that is 456.3 meter per second, right. We will take the specific volume also at throat. Specific volume at throat is quality multiplied by saturated vapor specific volume. Now, why we are doing this? We are doing this to find the mass flow rate for each nozzle, because unless we have mass flow rate, we cannot find the power output. Velocity diagram will give us only the power output, let us say, per unit mass flow rate. So, in order to find the power output, we have to have mass flow rate of the steam. For the mass flow rate of steam, we need the cross section area, and cross section area is given only for the nozzle, right. So, for this reason, at the nozzle throat, cross section at the nozzle, cross section of the nozzle at the throat is given. So, at the throat we have area, we have calculated the velocity from using this formula. This V is equal to under root 2000 H1 minus H2. We have taken 1000 because specific enthalpies are in kilojoules. Now, area is with us, velocity also we have found, specific volume is equal to X Vs, this we have taken from here 575 Vf, VFG, Vg, yes, this multiplied by quality of the vapor, right. Now, from here we can find the mass flow rate per unit nozzle. So, mass flow rate per unit nozzle is 0.029 kg per second. Now, if you look at the numerical, how many nozzles are there? Are 4 nozzles. So, this mass flow rate is multiplied by 4, right. When this mass flow rate is multiplied by 4, we will get the cross mass flow rate. Once we get the gross mass flow rate and then multiplied by VW is known, U is known, divided by 1000, we will get the output of the turbine. And this output of the turbine here in this case is 40 kilowatts. So, this is one numerical I have solved for impulse turbine. Now, another numerical I will solve for impulse reaction turbine. Now, here the total tangential force is given. Total tangential force on a ring of Parsons turbine is 1000 newtons. Remember, in Parsons turbine, the characteristic of the Parcel turbine is absolute velocity as inlet is equal to relative velocity at outlet. I explained it earlier. 1000 newtons. When the blade speed is 100 meters per second, blade speed is u. The mass flow rate is 8 per kg per second. The blade outlet angle is 20 degree. This is the outlet angle of the blade. Determine the steam velocity at outlet from the blades. If friction losses which would occur with pure impulse are 25% of the kinetic energy, here 25 carry this friction losses have come into the picture, corresponding to the relative velocity at entry to each ring of blades, because Parcel turbine has number of stages. So, here we are talking about one stage. The loss are 10% of the heat drop in the blade. Determine the heat drop per stage and the stage efficiency. Okay. So, for this so for this the force is 1000 Newton. Right, which is working on the blades, and blade peripheral velocity is u is 100 meters per second. There are two things. Blade inlet, nozzle inlet angle is equal to blade outlet angle 20 degree. They are all given values in numerical. Now F and mass flow rate is also given 8 kg per second. So here now F is equal to mass flow rate into VW. So from here we can get the value of VW, that is equal to 1000 divided by 8, 125 meters per second. If you look at the triangle, velocity triangle for a Parcel turbine, this is U, this is V1, this is VR1, this is VR2, this is V2, and this is alpha 1 and this is beta 2. They are known 20 degree, right? But what we don't know, the beta 1. Now here, in order to find beta 1, let us find the value of x and y. Now the x is V1 cos alpha 1 minus u. Now V1 is known to us. Yes, and y is V1 sin alpha 1, right? Or we can say x is equal to V W minus u divided by VW minus u divided by 2. X is VW divided by 2 minus u by 2. VW divided by 2, this is VW divided by 2. Half of this because the Parcel turbine symmetry, both symmetries is on both the sides, right? Minus u by 2. So, we will get this. Y is equal to VW. So, y is equal to this plus this tan alpha 1. So, let us take this z tan alpha 1. Now, z is this length plus this length. So, this length is VW by 2 and this length is u by 2. So, z is equal to VW plus u by 2, right, and this is 10 and this will be y is going to be 10 20, this 10 20. Now from here we will get the value of x. Here we are getting the value of x as 12.5 meter per second and y the value is 40.95, right. Once we have the value of x and y, we can find the value of beta 1. Once the value of beta 1 is known, we can find the value of alpha 2, right, and the V1 is V1 is 112. This is this V1. So V1 cos alpha. Sorry, this is V1 cos alpha 1 is equal to this VWU plus VW plus U by 2. This is VW by 2 plus U by 2. So VW plus U by 2. These values are known. From here we will get the value of V1. Now, once the value of V1 is known, that V1 is 119.7 meters per second. Delta H isentropic in nozzle is equal to delta H isentropic in blades, because reaction is, degree of reaction is half in Parsons turbine. So, delta H in nozzle divided by delta H in nozzle plus delta H in blade is equal to half. From here we can get this expression and that is equal to Vn square minus phi Vn square by 2 efficiency of nozzle. So, from here we will get 119.7 square minus 0. Carryover coefficient is given 0.0 into 42.8 square divided by 2 into 0.9 into 1000. 0.9 is taken from here. The expansion losses are 10%. So, 0.9 is taken from here and 42.8 is the velocity. This is VR2 and this is 119 is the velocity V1, right. So, this is V1 square minus 5 VR2 square, because here, right, and from here we get the delta H blade as equal to 7.2 kilojoules per kg. So, total delta H is going to be 2 times 7.2, and here if we want to calculate the gross stage efficiency, it is going to be 125 into 100 divided by 14.4 into 1000 and it is going to be 0.868 or 86.8%, right. So, the gross stage efficiency is 86.8%. This is the last value which we are supposed to derive out of this numerical. Here there is a correction. This is VR2 square and this is VR1 square, because carryover coefficient, when we talk about the carryover coefficient, this is VR1 square and this is VR2 square. So, this is there is a correction. This is V1 and this is equal to VR2 in a Parsons turbine. So, VR2 square minus 5 VR1 square divided by 2 into 0.9 divided by 1000, and this is going to give us the value as pressure drop, this enthalpy drop in nozzle as 7.2. That is all for today. Thank you very much.